Alright friends, welcome back. In this video we're going to go ahead and move on in our discussions of Chapter 5 and take a look at the second section of Chapter 5, which is going to be a discussion of logarithms. And so what I want to do in this video is give you a brief reintroduction to what a logarithm is, how we can go ahead and differentiate that from an exponential, and then how we can also go ahead and use our skills to evaluate logarithms, both with and without a calculator. So let's dive into that, right? So first of all, what is a logarithm? A logarithm is basically a concept in mathematics that asks this question, right? So the question that it asks is, for example, how many 2's multiply to make 8? Okay, so if you think about that, if you think about how many copies of 2 would you need to multiply all out together to make an 8, what you're basically wondering is, what is the exponent on this expression going to have to be, right? 2 to the power of what is going to be equal to 8, okay? Well, obviously, if you think about that for a minute, that is going to be the exponent, and that's going to be an exponent of 3. It's going to take 3 copies of 2 to multiply all out to make an 8, okay? If you see a logarithm, if you see log written on your page, then I want you to think back to this exact same situation where we're basically just asking this very, very simple question. How many 2's fit into an 8? Of course, there's nothing special about 2 and 8 here other than to just demonstrate how this works. You know, how many copies of 4 fit in 64? How many copies of 5 multiply out to make 125. We're going to see a lot of different examples in this video, but that's always the essential question, and we'll revisit that as we take a look at some future examples here. But the logarithm basically just stresses what the exponent is, which means that if we kind of relate this back to what we just finished talking about, exponentials, we basically have in our hands here 2 different languages for being able to say the exact same statement. Both of these statements that you see here, the 2 cubed equals 8 and log base 2 of 8 equals 3, these are the exact same statement. They're just said in 2 different languages. One is in the language of exponentials, the other is in the language of logarithms, okay? And you see how you can translate from one to the other. Basically, what we would like to emphasize here is that the exponential, we talked about in the previous videos, has a base number of 2, and logarithms, we're going to find, are also going to have a base, and those bases are actually the exact same in both languages. So the base of the exponential is the base of the logarithm. You're going to hear me say that a lot. And then what you see here is that what the logarithm again asks is, how many copies of 2 multiply to make the number that comes next, which of course is 8. And if we think about that, we of course know that that's going to be 3, and that number of course is going to be the exponent of what we had in the exponential form. So you're also going to hear me say a lot that logarithms are just exponents, okay? They represent the exponent in that essential question that we saw from before. And again, there's nothing special about the specific example with 2 and 8 and 3. We can take this to the general case by just kind of introducing some variables, but this is going to be the exact way that we can translate between exponential and logarithm languages by using this little mapping here. Another way to say that is just simply right here. Again, can't emphasize this enough. The base of the exponential is going to be the base of the logarithm, and then whatever you get as what is equal to the logarithm, that is always going to be the exponent that you have over in the other language here. And so what I want to do first is take care of example 1, where it just simply says rewrite the logarithm equation in exponential form. So we're basically just translating the language over to the other. And so an easy way to do this would be to go ahead and emphasize first here that, again, the base of the logarithm is the same as the base of the exponential. And so the base of the logarithm that we've got here is, of course, 3. And so when we write this in its exponential form, we're going to start off with a base of 3. We're going to raise that 3 to some exponent, and it's going to be equal to the other number that we've got going on here, okay? Well, one of the easy ways that you can go ahead and remember this is to go ahead and remember this whole looping around idea, okay? So if you have something that is started off in logarithm language, then we can go ahead and simply take that base of the logarithm and follow the order that I'm about to demonstrate here, right? We can say here simply 3 to the power of 2 is equal to 9, okay? So 3 to the power of 2 is equal to 9 would be a statement that says the exact same thing as the logarithm that we were presented with here, but it's saying it using a different language than logarithms. It's saying it using the language of exponentials. And so 3 squared is actually equal to 9. That is a true statement. And so whenever you write a statement out, it pays to just kind of take a look at it and ask yourself if that actually makes sense. And it does, because it does say 2 copies of 3 multiply out to make 9. And if you take this back to what we were saying earlier, right, what does a logarithm ask? It says, how many copies of 3 multiply to make 9? We know that that's going to be 2 copies of 3 because 3 squared is equal to 9, okay? Moving right along here, we have another logarithm. Again, we might ask ourselves the question, how many copies of 8 multiply to make a 1, okay? And that's a little bit of an odd question here, but again, if we follow that whole looping around order that we just discussed, then we can go ahead and convert this really easily. 8 to the power of 0 is going to be equal to 1. All right, and so writing it in its exponential form, we could say that 8 to the power of 0 is equal to 1, in which case we could just see that this is translated into a statement that is a little bit more reminiscent of the zero exponent property that we saw back in chapter P of this year. Okay, another logarithm statement here. So we have here a base of 5 to our logarithm. We're going to go ahead and loop this around to translate. So 5 to the power of negative 2 is equal to the fraction 1 over 25. So this would be a demonstration of the negative exponent rule. Remember that a negative exponent basically takes the base, which right now is a 5, or 5 over 1, and reciprocates it into 1 over 5, and then we apply that exponent of 2, calling that 1 over 25. Okay, so really easy to be able to convert back and forth between logarithms and exponentials. So let's maybe go the other way around, right? So let's maybe now start with a statement that is written in its exponential form and write an equivalent statement using the language of logarithms, okay? Well, obviously, the first thing that we're going to need for each one of these examples is we're going to need to write down the log, because we're dealing with a log, right? But we now need to go ahead and remember that the base of the exponential is the exact same as the base of the logarithm. And so if the exponential has a base of 6, then the logarithm is also going to have a base of 6. And the nice thing about remembering the whole looping around trick is that it works the same way going in the opposite direction as well. If we just simply start off here with a base of 6, we could say the log base 6 of 36 is equal to 2, and that would be a really easy way to go ahead and remember the order that we need to preserve whenever we translate, right? So log base 6 of 36, written just like that. Again, the question that this is asking is how many copies of 6 do you need to multiply into a 36? Well, of course, we would need 2 copies of 6. And so that would be the way to write that equivalently using the language of logarithms. Doing this next one here, we have a base number of 16. Again, that whole looping around action here yet again. Log base 16 of 1 over 16 is equal to negative 1. Okay, so log base 16 of 1 over 16. How many copies of 16 do you need to multiply into a 1 over 16? Might be a little bit of an awkward question to think about until you remember the whole looping around action and see here that's going to give us negative 1. And so this is where we kind of have to maybe interpret what we talked about before in a little bit of a different way and maybe just stick strictly to this whole looping around action that we see here. Last one here, so we have a log with a base that is the same as the base of our exponential here. So that's going to be a log base 125 of 25 is equal to the fraction 2/3. Okay. Now, one typical thing that you might see in some textbooks and online resources is that just to emphasize what is the input and what's the base, especially if stuff is being handwritten and everybody's handwriting is different, what we typically also go ahead and see here is that we can put parentheses around that input to just simply emphasize that that's the input of log, and the other number that you see there, of course, is the base, okay? But really, really easy to translate back and forth between exponentials and logarithms, and again, that is going to be a step that we're going to need to be sure to perform to make future problems involving logarithms that much easier for us to do. What I want to do here in example 3 is I want to evaluate these expressions involving logs, but I'd also like to do them without using a calculator. We'll move on to the calculator case here in just a moment, but here in example 1, we basically just want to go ahead and evaluate what the log base 3 of 81 is, and the way we're going to do this without a calculator is we're going to remember what the question was that logarithms were asking, right? The base number is a 3, so we're asking ourselves how many copies of 3 multiply to make 81? Okay. Another way that you might ask that question is to maybe say that this is equal to some number. You can give it like a variable name, maybe call it x. I'm just going to draw one of these dot boxes here. But the log base 3 of 81 is going to be equal to something. And so now if you go ahead and translate this using that looping around trick that we just talked about, we can go ahead and translate this into its exponential form by going ahead and saying 3 to some power is equal to 81. So it asks the same question again. How many copies of 3 do you multiply together to make 81? Well, if you think about that, if I just have one copy of 3, that doesn't get us up to 81, obviously. So maybe introduce a second copy that we multiply on. That would make 9 by itself. maybe introduce a third copy of 3. That would make 27. Can't get up to 81 just yet until we introduce a fourth copy. 4 copies of 3 are going to multiply out to make 81. And so we know that the log base 3 of 81 is simply just going to be 4, because that's how many copies of 3 it took to multiply into 81. And of course, if you were to go through and actually translate this logarithm expression to its exponential form, you would see that this translates into 3 to the 4th power is equal to 81, which is actually a true statement. And that, again, could be a way that you check yourself as you continue to work with logarithms in this way. The next one, part B, how many copies of 2 multiply into 16? Okay, so if I go ahead and give this maybe like a variable name instead of a dot box, like maybe go ahead and call this x, and then go ahead and do my whole looping around action, maybe saying here 2 to the power of x is equal to 16, it asks the same question. And so you might just go ahead and do that mentally. If you start off with 1 copy of 2, that's obviously not going to get you up to a 16, so maybe introduce another, that gets you up to 4, introduce another, that gets you up to 8, and then introduce another, that finally gets you up to 16. So because it took 4 copies, we could say this. We could say the log base 2 of 16 is equal to 4, because that's how many copies of 2 it took to multiply to 16. Last example here, again, same thing. I might just go ahead and informally just kind of think about this one. We know that the deal is now, right? We want to go ahead and figure out how many copies of 4 multiply to make 64. Well, 1 copy is not going to do it by itself, so let's introduce another. That gets us up to 16, and let's introduce a third copy and see if we get up to 64. So that would be 16 times 4, and that, of course, gets us up to 64. So it only took 3 copies of 4, and so that is why the log base 4 of 64 is equal to 3. Okay, and so again, what a logarithm is just an operation that basically just simply asks that very simple question: how many copies of the base multiply into the input? Now, we could go ahead and do a lot of logs without using a calculator, but what you're going to find is that there are going to be some logs that we definitely want to go ahead and use a calculator to perform, especially ones that don't fit that analogy of how many copies of one multiply into the other sort of scenario, right? So you're going to find that in basically all scientific calculators, there's going to be 2 types of logarithms that are hard programmed into the calculator, and they probably have dedicated buttons as well. So this is something called your common log and your natural log. And basically what sets these logs apart is just how frequently they come up in natural mathematics, right? So the common log is something that has a base of 10, okay? And so what we do is we give this a special notation, and we just go ahead and call this log without a base number written there. So if you ever see that, then I want you to think of this right here. If you don't see a base, then automatically just simply assume that it's 10, and again, that's called the common log, okay? Now, different from the natural logarithm, which actually has a base of Euler's number, which is something that we talked about in the previous video. That is going to be that number that we get as we let n be bigger and bigger in that compound interest scenario. And so we give that a special notation here. We call that ln, and you might kind of beg the question here, well, if it's called the natural log, why don't we call it the nl? Well, what we want to do is focus with our notation and emphasize here that what we're dealing with is a logarithm. And so that's why we typically go ahead and write this so that the L comes first, so that we're always able to remember that that is a logarithm, okay? And again, that's just simply a log with a base of e, but instead of writing that, because it comes up so naturally in mathematics, we typically just go ahead and give this special name to it and call it ln. And again, these are hard programmed into your calculator, so you can see here that as I go ahead and move on here to the next example, where it's basically just asking us to use the calculator to evaluate, you can see that I've already gone ahead and got my calculator pulled up here. Let's go ahead and talk about how to type that in. The log button on the TI-84 is sitting right here next to 7. Again, that's your common log because you don't see a base. We just simply want to go ahead and type in a 5, and it automatically performs the log base 10 of 5, which is going to give us this decimal right here. So the common log of 5 is approximately 0.699 if we round to 3 decimal places. The natural log button is sitting right beneath that button here. And so we can go ahead and do the natural log of 0.1, which is our next example there. And we're going to find that when we press enter here, we're actually going to get a negative result, which is perfectly fine. It just has to do with translating that to the exponential form and working with negative exponents, which we can always do. And so those would be the buttons that we would want to press to go ahead and perform a log calculation. Also handy to know is that if you're in the TI-84, you can actually perform a calculation of a log with any base in any input, okay? You will have to remember the sequence of buttons, so if you want to write this down, then I would encourage you to do that, but you would have to press alpha, which is the green button on the calculator, window, which is the one of these 5 buttons up at the top, and if you press alpha window, you'll notice that it brings up this little menu here, and we just want the 5th item in that menu, so we're just going to immediately press the number 5 key, because it's the 5th item in that menu, and it automatically pulls it up for us. So again, that's alpha window 5, and that automatically pulls up for you this function in the TID4 that gives you the ability to calculate the log of any base of any input, okay? So if we wanted to go ahead and do that, we could, of course, evaluate something like it says here in example 5, where it says log base 6 of 15. We could just simply type in a 6 for the base, arrow over, 15 is the input, press enter, and it gives us the result nice and easy. But let's say you don't have access to a TID4, right? So you don't have a physical one, and for whatever reason you haven't downloaded the emulator on your tablet just yet, right? Well, there is a way that you can go ahead and use just a normal calculator instead of the TID4 to go ahead and do calculations like this. What it's going to mean, though, is you're going to have to use a special formula, and that formula is something that we call the change of base formula, okay? And so the way that this works, right, is the example that we just did is we wanted to figure out what log base 6 of 15 is. And so figuring that out real quick, we can see here that the way that the numbers are going to map around as we go ahead and apply the formula is that we basically just take a log base b of the input, which is 15, and we divide that by the log base b of the base, which is going to be that number 6. Now the question is, what is this number b? That number b could be anything. It could be 10, it could be Euler's number, it could be 64 billion if you wanted it to. But the reason that this gives you the ability to do calculations like this in any calculator is because you can be specific with your choice of b and specifically choose either the common log or the natural log to perform that calculation. And so what I mean to say here is that you could take log base 6 of 15 and you could do it in one of 2 ways. You could either look at this as the common log of 15 divided by the common log of 6, or you could look at this as the natural log of 15 divided by the natural log of 6. Regardless of which one of these you pick, you're going to get the exact same result in the calculator that we got by using that fancy trick in the TID4. So let's see that, right? Let's do the common log. That'll be the common log of 15 over the common log of 6. And if I press enter there, you can go ahead and match up the decimal to the one previously before it, and you can see that it's the exact same number. So even if you don't have that functionality in your calculator, you could still go ahead and get these results. Again, we can even have chosen to do the natural log here. So the natural log of 15 over the natural log of 6. Pressing enter, we get the exact same result. And again, just to prove this to you, if I go ahead and pick a different base here, right? Like maybe let's say here I do, let me go ahead and pull that up here, a log base 1000. I'm just making up 1000, right? As long as I do log of the input over log of the base, I'm always going to get the exact result that I need to get. So as long as I keep those base numbers the same, if I've got a base of 1000 on top and a base of 1000 on bottom, and then press enter here, you can see here that that's going to give us the exact same result as all the rest will. Now, it's obviously going to be pretty tedious to have to do 1000, so stick with the common log button or the natural log button in your calculator to give you those nice, easy results. Okay, we could even do other ones like this, like log base 3 of 7. So we'll just do this one last one, and then we'll call it a video here. So alpha window 5. So log base 3 of 7 will give us this decimal approximation right here. We can go ahead and use that change of base formula with our common log. So common log of the input over the common log of the base. We can see that we get the exact same thing. And we can, of course, also use the natural log here. So the natural log of the input, oops, I accidentally typed in second ln, which we talked about in the last video. That is actually something that gives you e to the power of, but that's not what we're interested in here. We just want to simply do the natural log of 7 over the natural log of 4 and press enter. Oh, I accidentally did 4. My bad. Let's see here. Let's fix that. So we have this, and then we've got this. And again, those results are the exact same. but let me type this next one in correctly here. So I don't know where I got 4 from. Let's type 3 like it should be, and we see we get the exact same result. There we go. Okay, so again, if you guys are ever trying to evaluate a logarithm, then you can use that change of base formula if you don't have that functionality in your calculator. But that's going to do it for this one. So again, just a basic reintroduction to the world of logarithms, what they are, what question do they ask, and how can we answer that question both with the calculator and without the calculator. So I hope this video has been helpful to you. If you guys have any questions whatsoever, as always, feel free to let me know. But that's all I have for this one. Thank you very much for your attention, and I'll speak to you in the next one.